In this video, we'll discuss the distinction between two important rate-dependent distributions, namely the Poisson and the exponential distributions. We'll start with this PowerPoint slide and then move on to an Excel live demonstration. First off, the Poisson and exponential distributions are very similar, with the primary distinction being that Poisson is used to forecast the number of events in a time interval, whereas exponential distributions forecast the time between events. An exponential distribution can also be used to model both size distributions and rate decline, such as oil well production. ARPS in 1945 established formulas to model exponential, harmonic, and hyperbolic decline curves that we'll discuss later in more detail. The table below summarizes basic requirements and characteristics for exponential and Poisson distributions, while the charts on the left give examples. Three requirements must be met to model either an exponential or Poisson distribution. The time between events must be known and constant over time. Second, events are independent. And lastly, events cannot be simultaneous. In this sense, these are Bernoulli trials. They either happen or they don't happen. Exponential distributions can also represent size distributions, such as oil field size. It can be argued that many exponential size distributions are modeled as log normal because of numerous entities are too small to be detected. For example, small oil accumulations are generally referred to as a show and not included in an oil field size distribution. Now let's compare some of the characteristics. As already mentioned, exponential distributions ask about the time between events, whereas Poisson asks about the number of events in a time period. As an example of an exponential, let's consider the lifespan of a lawn blower, where the average lifespan is 5 years. We can calculate the rate constant, lambda, as 1 over the average lifespan, mu, equaling 0.2, and plug this into the exponential formula to evaluate values of x, which in this case is years. The formula for the exceedance probability is given as the probability of x greater than some time equals Euler's number raised to the negative lambda times the time, t. Looking at the chart, there is a 20% chance that the lawn blower will last more than 8 years. While the exponential rate constant is 1 over time, Poisson rate constant is simply the average or expected number of events. As a Poisson example, consider the number of storms per year. On average, a city experiences 2 storms per year, mu. We can calculate the probability of any given number of storms in a year using the formula shown here. But Excel's built-in function is much easier. The chart shows, for example, that the probability of 3 storms in a year is about 18%, or there is a 14% chance of more than 3 storms per year, as read on the exceedance probability axis. Also note that the exponential curve, time, is continuous, whereas the Poisson number of events is discrete. Furthermore, the Excel curve steadily increases or decreases, whereas the Poisson distribution can have various shapes. Now let's look how these distributions are modeled in Excel. In the remainder of this video, we're going to look at 2 worksheets, one examining the exponential distributions and the other looking at the Poisson. In this particular worksheet on the exponential, we're going to look at the workflow for fitting an exponential distribution, calculating an exceedance probability using both the formula and Excel's built-in function, and fitting a size distribution. The workflow for fitting an exponential curve was found at Charles Zonnet's realstatistics.com worksheet. In this first example, I've set up an exponent and a series of IDs and calculated some x values using this exponent, as you can see here in the formula toolbar. Next, I calculate the delta. In the first row, it's simply the x value, but in the remaining rows, it's just the x value minus the previous x value. Again, we can see that in the formula toolbar. Next, we can apply the built-in Excel function here for expon.dist, where it uses an x value, and then it needs a lambda and a cumulative. Well, what is this lambda? To get at lambda, we take the mean delta, which is just the average of the deltas, and then the rate constant is simply 1 over lambda. Now that we have the rate constant, let's check out the formula. So in this column here, D, we've calculated the cumulative distribution, which is we used a cumulative of true. So let's check out the formula. And so we use the x value, then we apply the rate constant, and we set cum to true. And what we get is this orange curve here. Which goes from 0 to 1. So that's the cumulative probability. But if we set the formula bar to false, then we can get the mass density. So let's have a look at this curve. And there's our mass density for an exponent of 2. Note that the equation of this line here, it uses the rate constant raised to the exponent of minus the rate constant times the x value. Up here I've put the generalized formula for the exponential distribution. In this particular worksheet I've set it so that you could change the exponent to play around. So let's just make this a 5 and see what happens. And you can see that the x values are now much larger than they were. We'll set this back to 2 and hit Shift F9, recalculate. Another interesting thing about this is that the gamma function in Excel can also be used to calculate the x values. And you can see here it's just the, you just take the probability, and it's, you use for your shape factors, it's 1 plus 1 over the rate constant. And if you compare this column to our x values, you'll see that we recalculated them. For fun, I've set up a model here where I set up a range of probabilities going from a very small number to a very large number. And then I've calculated the x values for those probabilities using the gamma function, as we looked at a little while ago. And then I've used the Excel built-in expon.dist function to calculate the mass density, which basically gets me the same answer as this blue line. Now let's examine the lawn blower example. This is the same example that we saw in the PowerPoint slide, and we'll just start with the beginning here. We see that lawn blowers on average last about 5 years, and the lifespan follows the exponential distribution. So we want to know what's the probability that the lawn blower will last more than 10 years. In this worksheet we have 2 inputs. We have the x value, and we have mu, the average lifespan. And we again can calculate the rate constant lambda by just taking 1 over mu. In these gray cells we answer 3 questions. What is the probability that the lawn blower will last greater than 10 years? In which case it's an exceedance probability, or 1 minus the expon dist with x, mu, and the cumulative equal to true. We can answer the question of what's the probability of the lawn blower lasting exactly 10 years, which is just the mass density function. And then we can ask what's the probability of the lawn blower lasting less than 10 years, which is the expon.dist with the x value, mu, and the cumulative equal to true. I've also charted up for a range of time values for the life of the lawn blower, and I've done it a few ways. So I've set up this table going from 0 to 15 years, and I've done the calculation for the mass density, for the cumulative probability, and here's the exceedance probability. But I've also done it for by the formula method. just to show you that it's a little bit easier to calculate using Excel's built-in function. And then just a little bit lower in this worksheet, I've calculated the probability that the lawn blower will last more than 4 years but less than 7. I've done the calculation using the cumulative probability and the exceedance probability to demonstrate that either parameter will yield the same answer. Now let's move on to fitting an exponential size distribution. In this example, we'll look at fitting an exponential PDF to the top 100 producing U.S. oil fields. First, let's take a look at this chart here, where we'll examine different workflows for deriving the fitted solution. The orange squares represent the frequency, or sort of like a histogram, where I've made 21 bins. And you can see here's the data here, where I've binned the data using a frequency distribution. The data for charting these lines is over here on the right, where I've set up a series of probabilities going from 0.001 to 0.999, and using different methods I've calculated the distributions. The blue line represents the data set with all the data points without any binning, whereas the other three methods represent the bin data, which indicates that the binning helps to fit the data more precisely. In my opinion, the binned answers seem to fit the data better, particularly in this 15,000 to 100,000 barrel range. None of the methods quite get the 2 initial points. So let's back up and take a look here at what I've done. Initially, I used the Zionit's RealClearStatistics.com methodology. So here's the data, and here I've sorted the data from smallest to largest, calculated the delta, then used the exponential dist functions to get the cumulative and the in values, and here I've used that gamma function again to check the values. Then I've calculated the mean delta and just taken 1 over the mean delta to get the lambda, or the rate constant. For charting it, I've just simplified those by putting the lambda and the rate constant over here and used it to calculate in this table here for charting. So my initial view of this blue line, or the Zionit's method, I found what's not a very satisfying answer to the fit. So to check it out more fully, I imported the data set into Python. The green line represents the Python solution. So I just took the lambda and the delta mean from Python and charted it and found that it was much better, which raised the question, well, why does this work better than using all the data? So what happens in Python is it bins the data when it tries to solve for this. And the question is, but what is the optimal number of bins to use? As it turns out, in Python, it has 8 different methods for calculating the number of bins. And when I looked at it, I could find the formulas. So there are a number of methods that work. It seems that Python is using this Friedman-Diaconis calculation. Here I've given you the formula for doing this, and I've calculated out the bin width and then divided it by the range of the data to find the number of bins. Note that the Friedman-Diaconis calculation uses the interquartile range and the number of observations and yields 22 bins. Another common method is the Scott method, and it uses the standard deviation of the data and again the number of observations, but it gives 8 bins. Another common method is the Sturgis method, which just is the log 2 plus 1 of the number of observations, and again gives 8 bins. To see how this works, I've implemented the Friedman-Diaconis calculation or method and the Scott and the Sturgis method. That is, I've used 22 bins and 8 bins. So if we go back and we look at these charts, at the chart again, it seems to me that the bin methods seem to fit the data better. So let's take a look here in more detail on how I implement this. So here's the Friedman-Diaconis method, and I've created 22 bins. Here are the x values, calculated the delta x and the frequencies, and I've calculated the weighted mean and the rate constant. Let's take a look at this weighted mean. Here I've used this technique where I used the sum product and divided it by the sum of the frequency. And 1 over the weighted mean will give me the rate constant, or lambda. And then I've done the same thing here with the Scott method, again using that sum product technique, and calculated the lambda, or rate constant. And I've just used them up here in this table for charting. Again, it's my opinion that the Friedman-Diaconis method gives a better answer. That is, it has more bins and it looks more like the Python and fits the data better. So when fitting an exponential curve and you have an extensive data set, I strongly suggest that you bin your data to get a better fit of the data. Now let's take a look at the Poisson worksheet. Poisson distributions have a wide variety of uses in business, engineering, and sciences, including geological sciences. Geological examples include the probability of X number of storms in a year, or river flooding events, or volcanic eruptions and earthquakes. We'll explore these examples in this worksheet. Bounded and discrete, the Poisson distribution provides the probability of an event happening in a fixed interval of time, given the rate average number of events in a time period. The mean number of events is sometimes called mu, or lambda. The Poisson discrete distribution is given by the formula where p of some x number of values given an average of mu equals Euler's number raised to the minus mu times mu raised to the x number of events divided by the factorial of x. Excel uses the Poisson dist function to calculate the probability where Poisson.dist equals x number of events times the mean number, where cumulative can be true or false. It works for all positive values and is related to the exponential distribution, that is, evaluates rate. However, Poisson distributions, unlike the exponential distribution, are not restricted to the increasing or decreasing exponential shape, as we see in the chart below. So let's try some different values in this chart. Right now it's set to 2, and we could see that the histogram has more or less a log normal type of shape. Let's try a value of 0.2. Enter Shift F9, and you can see it almost looks exponential. Now let's try a value of 4. Shift F9, and it looks almost like a normal distribution. Now let's try a value of 10. Shift F9, and you can see it looks like a reverse exponential. So this demonstrates that the Poisson shapes can vary, unlike the exponential. Moving on to our first example, we'll look at the number of storms per year. The average number of major storms in your city is 2 per year. What is the probability that exactly 3 storms will hit your city next year? To figure this out, the first thing we need to do is we need to know what the average number of storms per year is historically, and it's set to 2. The next thing we need to know is what do we want to evaluate for? And here we're going to evaluate for 3 storms per year. And we need to know Euler's number, which is approximately 2.71828. We can plug that into the formula, as I show here, and work out the problem. And we get a value of 0.18. And I've done this up here, and you can look at the formula as it is in the worksheet, or we can use Excel's built-in function. As it turns out, the probability of 3 storms per year is 0.18. The chart on the left expands on this and shows the probability of 0 to 8 storms in a year. We can see that the probability of 3 storms in a year is 0.18, as we've shown in the calculations previously. But we can also see that the exceedance probability, which is 1 minus the cumulative probability, says that there is a probability of roughly 14% of 3 or more storms in a year. For a really good explanation of the Poisson distributions, I strongly suggest Stephanie Glenn's site at statisticshowto.com, which I've left a link for. Now let's move on to example 2, Mauna Loa volcanic eruptions. Our Poisson question is, Mauna Loa volcano erupted 37 times over a 118-year period from 1832 to 1950. What's the probability of 2 eruptions next year? For mu, we find the average number of eruptions by dividing 27 eruptions in 118 years. And we evaluate for 2 eruptions. Again, we calculate the answer using both the formula and Excel's function, and see that there is a 3.6% probability of 2 eruptions next year. The table and chart show that there is a 73% chance of 0 eruptions. We can also say there is a 27% chance of 1 or more eruptions next year. We also see that there is a 23% chance of 1 eruption in a year, a 3.6% chance of 2 eruptions, and so on. It is interesting to note that the distribution of eruptions takes on an exponential distribution, as we can see in the bar chart. Below, from cknewtson.com, was the analysis of eruptions by month and fitted to an exponential distribution. I have therefore twisted the analysis to an exponential question. That is, what is the probability of an eruption in exactly 12 months? But of course, this could be any time frame, for example, 15, 18, or 20 months, and so on. Notice that no matter what x value is, lambda does not change because it is derived from the fitting exponential distribution. Hence, the probability table and chart do not change with the x values evaluated. So we can answer the question thus. There is a 2% chance of an eruption in 12 months' time, or there is a 27.7% chance of an eruption will occur within the 12-month period. Note that I also solved the probability using the gamma function to demonstrate that it is related to the exponential function and yields the same answer of 2% probability. Now let's move on to the third example. What's the chance of 1 significant earthquake in Los Angeles County per year? We have a record of 20 significant earthquakes in Los Angeles County in a 245-year period from 1769 to 2014, which gives an average of 0.082 earthquakes per year. I've also added the mean delta and exponential rate exponent in the case that an exponential analysis is desired. Scrolling down, we can see that the Poisson analysis shows a 7.5% chance of 1 significant earthquake per year, and the table and the chart show, for example, a 92% chance of 0 earthquakes per year, and so on. I guess Los Angeles County is a much safer place to live than I thought, at least with respect to significant earthquakes. This concludes this video. Thanks for listening. Like and subscribe.